Hello everyone, welcome back to PMAC1140. In this video, I will be discussing the last function in college algebra. Last time, we already learned exponential function, and you guys know the exponential function is the curve, is this increasing curve or decreasing curve. So before we start with logarithmic function, let's do a quick recall on exponential function. Okay, so I'm going to use this recall. So last time we talked about exponential function f of x equal to a b to the x. Okay, and we know that exponential function will be something like this. For b is greater than 1 and if b between 0 and 1, we have this decreasing curve, right? And the domain of this function is from negative infinity to positive infinity. Okay, now I want you to look at this. I'm going to go ahead and draw a line. Okay, I draw a line. And this line is going through the origin at 45 degrees, and this line actually is y equal x. And I'm gonna mirror the exponential curve about this line. So if I go ahead and mirror them, so it's gonna be something like this, right? Here you go. It's gonna be something like this. Okay. So before we learn exponential function, we already learn inverse function. If two functions are inverse of each other, if they are reflected about the line y equal x. Okay, so actually the blue curve right here is actually the inverse function of the exponential function f of x a b to the x, and this inverse function here, we have another name, okay, for that. We call that log function. So g of x equal to log base b of x. Okay, so this is the log function here is the inverse function of exponential function, and they are inverse of each other. Okay, so in this section, I would like to discuss logarithmic function. In this video, so let me use an even color. I want to discuss log function. Okay, and log property. Okay. We'll be learning how to simplify a log expression using log property also. Okay, but on the first part of the lecture today, I would like to talk about log function first, and we're gonna discuss the domain and range of a log function. Okay. And we also talk about the log principle, which is very important. Later on, we will use that to solve log equation. So log function could be something as follows: f of x equal to log base b of x. So the b over here is called the base. B is the base. X here we call the argument. Okay, and the log could be increasing or decreasing. It depends on the b value. If b is greater than 1, okay, if b is greater than 1, sorry, Okay, b is greater than 1. We know that the log will be increasing function. So the sketch of the log function will be something like this. Here you go. Okay, that is for b is greater than 1. So you see over here, we have y-axis as the vertical asymptote. Okay. And if b is between 0 and 1, and we see that the log function will be decreasing. It will be something like this. Okay, this will be something like this. Here you go. Either case, the domain of the first case and the second case is still from 0 to positive infinity. The same thing over here, the domain will be from 0 to positive infinity. And we cannot, we're not going to go ahead and include 0 because we cannot take log base b of 0. We cannot define it. Okay. How about the range? The range will be negative infinity to positive infinity. The same thing over here. The range will be negative infinity to positive infinity. Okay. So based on this graph over here, we know that the argument x must be greater than 0. Okay. This fact is going to help us to find the domain of any log function. We just need to look at the argument of the log function, and we can find the domain easily. Okay. There's another thing I want you to notice is that because log function and exponential function, they are inverse of each other. So it means what? It means that from log function we can convert it to exponential form, or vice versa. Okay, this relation we call that log principle. Log principle. The log principle states that if y equal log base b of x, then this is equivalent to x equal to b to the y. There you go. This is very, very important, and I'm going to go ahead and box them. Okay, very important. Because we're going to use this to solve log equation later. Okay. Now let's take a look the first example. So I'm gonna hold on before we do the example. Let me put another remark. This is the first remark. The second remark is that log and exponential function are inverse of one another. I put it in yellow colors so that you can you can remember. This is very important fact. Okay. Now let's do the first example together. Okay. I can give you the example of the log function like this: f of x equal to how about log base 2 of x? Okay, so because the base over here is 2 and it's greater than 1, so we know that for sure that the sketch of this log function could be increasing. Okay, how about this one? I can give you another example of log function g of x equal to log base 10 of x. Okay, So for log base 10, we can use another way to write it. It's a short way. So we can go ahead, throw away the base, and we just need to write log x. So if they write log x, it means that it's log base 10 of x. Okay, and you can see this notation in your calculator. Any calculator, they always have this. But if you have a TI 8485, you can write log with any base you want. Okay. There's another special log function with base e, and e is 2.71. So if you have log base e of x, this is called natural log. But if they have log base e, nobody write like this. Usually they write lnx. Okay, lnx. So is if you put into your calculator, is about 2.71. So this is called natural lnx. Okay, good. Or I can have something with the base between 0 and 1. For example, I can have f of x equal to log base 1/3 of x. It still works. It still works. Actually, this is the same as, negative, because this is, I can rewrite it as 1/3. I can write it as 3 to negative 1 of x. Alright. And this is the same as negative log base 3 of x. It's interesting one, right? It's very interesting right over here. Okay, let me see. Let me check one more time if everything is correct. Now on the second example, I'm going to show you how to find domain of log function. Okay. Usually we can go ahead and sketch the graph of log function. We can look at a graph, a sketch, and we can read the domain easily. But what if they give you something like this? 2x minus 1 plus 5, and they're asking you to find domain of this log function. Well, if you have calculator, you can go ahead and grab them, and you can read the domain from the graph easily. But what if they want you to find the domain algebraically? So what we're gonna do? Everybody know that for this log function over here, it is transformed from the parents function, which is a transform from log base 3 of x. Okay, so over here they move 5 unit up, right, and move it to the right a half unit. Okay, so if they move it to the right a half unit, think about it. I just do a quick sketch. Okay, so this is 1 here. Okay, so this is 2 here. Okay, so we need to find the intersection point between, in order to sketch it, in order to graph it carefully, we need to find the intersection point between the curve and the x-axis. Okay, which is, you see that it's very hard for you to find. You know, it won't be easy until you learn how to solve log equation. But let's see, we can take a guess over here. We kind of estimate it. So think about it. If x equal to 0, if x equal to 0, so I'm gonna plug over here 2 times 0, 0, so it doesn't work, right? If x equal 1, what happened? If x equal 1, if x equal 1, 2 minus log 1 equals 0. So look like that the curve is gonna be something like this. It's gonna be something like that. I just sketched the curve by using a very traditional way of graphing, which is plug and upon. Okay. And I use calculator. Later I'm gonna show you how, but right now, because when you don't know the log property yet, so I just go ahead and draw this curve for you. Okay, so the sketch of this function will be something like this. Okay, later on when we talk about exponential property and log property, you can understand why they cut at 1 right here. Okay, now think about it. This one will be moved. Usually, this is the graph of this function. Okay, the parent function is log base 3 of x. It's a parent function. Okay, and it's gonna be moved. It's gonna be moved a half unit to the right. Okay, it's gonna be moved. It's gonna be moved a half unit to the right. Okay, because this is a transformation right over here. Okay, we already learned transformation concept, so it's gonna move half unit to the right. Okay. Okay, so the sketch right here, it represents this function, the parent function, not this one. Okay, not this one. All right. Now we're gonna move half unit to the right. So right now, the curve will be something like this, right? The curve will be something like this. All right, and the y asymptote will be something like this. So it's going to move half unit. Okay, and the curve will be something like this. There you go. It will be something like that. Now think about it. So the domain will be what? The domain will be something from what? Let me see. So the domain will be everything's greater than 0.5, because this is a half right here. This is 1, so over here is a half. Okay, so you see that if you can go ahead and sketch the parent function and apply the transformation curve, you can find the domain easily. Okay, but you can also find the domain by looking at the argument. So the argument over here is, will be 2x minus 1. Okay, and you just need to set it greater than 0. Okay, you set it greater than 0. Then my inequality 2x will be greater than 1, right? And x will be greater than a half. So from here I can get the domain will be what? It will be a half to positive infinity. Okay, so that is how you can find the domain of log function algebraically. You don't need to sketch. The reason I'm over here, I give you the sketch, because just for you to compare. It's going to be the same if you find a domain with the sketch and algebraically. But what if I put this on the test? Then you have to find the domain algebraically. This is what you have to solve. Okay? Good? Alright. Now, in order for you to sketch the graph, to do the sketch of any log function, you need to know how to evaluate the log function. You see over here in this example, I just go ahead and sketch it, and I did not tell you why I got at 1 right over here. Now, on the second part of the lecture, okay, the second part of the lecture, I will be talking about the log property. Okay, this log property is going to help you to evaluate a log function, or you can evaluate a log expression at certain x value easily. Okay. The first property is, if you have log base b of 1, which is give you 0. If you have log base b of b, this is give you 1. Okay. Number 3, if you have log base b of x to the n, then this is give you n times log base b of x. Number 4, if you have b raised to log base b of x, then this is give you x. Okay. Number 5. In the number 5 and number 6, usually we're going to use number 5 and number 6 when we try to simplify log expression. If we have log base b of x times y, then this gives you log base b of x, okay, plus log base b of y. Okay. Number 6. If you have log base b of x over y, then it's equal to log base b of x minus log base b of y. Alright, so there's only 6 properties here, and I want you to memorize it, because it's going to help you to evaluate log function. It's going to help you to sketch log function easily. Okay. Now let's take a look at this one. Let's do the first example here, and how we're going to use log property here to evaluate the log. Now, what if I want to evaluate log base 10, which is, I'm not going to go ahead and write a base, of 100,000. Okay, 100,000. Alright, so how I'm going to use the property here to evaluate this. So 100,000, I can rewrite it as 10 to the 5th power, right? Then I'm going to go ahead and apply the third formula. So there's the 5th power over here. The base b over here is 10. So I can drop down the exponent. So I can write this as 5 times log base 10 of 10. But if the base and the argument are the same, I can use the second formula here, the second property here, to write it as 1. So this is equal to 5 times 1 equal 5. There you go. Now, get back to the question over here, why I have the y curve over here intersect at x-axis at 1. Well, it's easily. I just go ahead over here, I replace x over here with 1. Think about it. If we have log base 3 of 1, which is give you 0. Alright? Log base 3 of 1 gives you 0. So the input is 1, the output is 0. So you have 0, you have 1, 0, which is this point. Okay, the coordinate of point over here is 1, 0. This is 1, 0, right there. Okay, so actually I use the log property here when I replace x over here with 1. And this turned out to be 0. So that is the point right there. Okay. Good. Okay. All right. Now, let's do another one. Example number 2. Now I want to evaluate log base 10 of 0.001. Okay. So let's see how we're going to do this. So first of all, this is a decimal number. I'm going to go ahead and change it to fraction. So this is 1 over 1,000. And 1,000, I can write it as 10 to the negative 3, right? Now I'm going to apply, look at this. I'm going to apply this one. So I'm going to apply the third formula again. Okay. So which is give you negative 3 log base 10 of 10. And log base 10 of 10, which is the first formula. Right. So your answer will be negative 3. Okay. Very easy. Okay. Of course, there's some of the number you cannot go ahead and evaluate the log manually. You have to use calculator, of course. Now let's do another one. Example number 3. How about I take natural log of 1 over e? Okay. So natural log of 1 over e, I can write this as natural log of e to the negative 1. So I can use the third formula again. I drop down negative 1, so I have natural log of e, and natural log of e, natural log is base e, so the base and the argument are the same, so give you 1, so which is negative 1 times 1, which is give you negative 1. Okay. Okay, how about this one? Number 4. What if I have 5 raised to log base 5 of c squared? So c squared plus 4 is the argument of this log, and the whole log over here is the exponent of the base 5 right here. Okay, so I'm going to apply what formula I'm going to apply. I'm going to use this one right here. The base and the base over here the same, so it give you the argument. So the base here, the base here the same, so which is just give you the argument, which is c squared plus 4. Okay. That's simple. Okay. Very easy. Now in the example number 5, I'm going to go back, give you another example of how to find domain of the log function. What if I have f of x function like this, log base 10, which is, I'm not going to go ahead and write a base, x squared minus 9. Okay. So I want to find domain of this one. Remember last time when we found how to find domain, we just need to set up the argument greater than 0. So the argument is right here. So x squared minus 9 greater than 0. Oh, so what is this? This is the concept we already learned like last week. This is nonlinear inequality. It's quadratic. It's nonlinear inequality. So you have to use the side table. But before we can use the side table, we have to go ahead and factor everything like that. Okay. Then I'm gonna put those value. So I'm gonna put the value over here. So I'm gonna solve for 2 value. Okay, so for these two values, so x equal -3 and x equal 3, I'm going to put these two values on the number line. Alright, remember, then there are three intervals. We're going to go ahead and check the sign by plugging the value. So let me plug it in really quick over here. So positive, negative, positive. Okay, so the question is, what we need is greater than. I'm sorry, what we need is greater than. So we're gonna go ahead and check this. So the domain of this will be what? Will be -3, not included because it's not equal to 3, not included. Okay. Okay, so on the third part of our lecture, I just want to show you how to use the property number 5 and property number 6 to expand and condense log property, condense log expression. What is log expression? Which is the mathematical expression contain logarithm. So expansion and condensing is like you want to rewrite a log as the sum, or you want to rewrite a log as a product. Remember in formula number 5 and number 6, we have the log of the product, which is give you the sum of two logs. We have a log of quotient, which give you the difference of two logs. Okay, so let's see how we're gonna do that. So over here I'm gonna put expanding and condensing log expression. Alright, so on the first part, let's talk about expansion first. Okay, let's talk about expansion. So when you expand a log, it means that you want to rewrite it. You want to break them apart. You want to rewrite it as a sum or the difference. You want to really break them down, all the way down. Okay, for example, I have the log like this: log base 2 of ax. Alright, ax, it means 8 times x, and we know that the log of the product give you the sum of two logs. So to give you the sum of log of each factor, so 8 and 6, 8 and x. So I can write it as log base 2 of 8 plus log base 2 of x. Okay, but look like that we already finished, but it's not, because we can break it down over here more. 8, I can rewrite it as log base 2 of 2 to the third power. Okay, and log base 2 of 2 to the third power, we already learned how to evaluate on the second part of the lecture. So I can drop it down here: 3 log base 2 of 2. This is the third formula, third property, log base 2 of x. And log base 2 of 2 give you 1, so 1 times 3 is 3. Log base 2 of x. There you go. So this is how you break it down. You have to break it down completely using the log property where we already talked about in the second part. Okay. And what if inside there are 3 factors multiplying each other? What happens? Well, you're gonna do the same thing. You do the same way. What if I have like this: log base 3 of 5xy. Alright, so I can break them up using property number 5. So give you log base 3 of 5 plus log base 3 of x plus log base 3 of y, and you cannot do anything else because this is the simplest form already. You cannot break anymore. No more breaking down. That's it. Okay, there's nothing else we can break more. All right, so that's gonna be your final answer. Now let's do something more complicated. Let's see how we're gonna break down this one. What if I have log space phi of a quotient z to the third over x, y, phi. Okay, so we know that the log of the quotient will be the difference of two logs. So first of all, I'm going to break it down. So it will be the difference of the log of the numerator minus the log of the denominator. Okay, and this one we can apply the third formula, third property. I can bring down the exponent, so become 3 log space phi of z. If you notice, this is the product, so I can use the number 5 formula. So right here, so let's show you one more time. This number 5, this number 6, and this number 3. Okay. Okay. So this is because when you break them down over here to give you the sum, and just in front of the sum is the minus, so we gotta put in parentheses, so it becomes log base phi of x plus log base phi of y to the 5th power. Okay. Then we can go ahead distribute the minus in, so we give you a log base phi of x minus log base phi of x of y to the 5th power. Okay, and now the exponent over here you can drop to the front, so become 3 log base phi of z minus log base phi of x minus phi times log base phi of y. There you go. So this is how you break it down completely. There's nothing else we can break more. Alright. Now let me give you this one. Example number 4 here. I have radical. Okay. Remember that one of the formula related to radical and rational expression, rational exponent, we already learned in intermediate algebra. So we have something like this. If we have n root of x to the m, we just give you to the x to the m over n. So we try to use this formula here to do expansion for the following log expression. So I have log base 10 of cube root. See that? And inside the root I have a fraction. Okay. Over 10. Okay. So first of all, we need to get rid of the radical by applying this formula here. So I can change the log base 10 bracket x, y to the 2nd power over 10. Okay, raised to let me see. I think I'm gonna break down one by one first. I think that's gonna be better. Okay, I'm sorry. We can do this, but it's gonna look more complicated to you. So I'm gonna break it down like this. So because it's the cube root of the fraction, we'll give you the cube root. So we'll give you the cube root of numerator and the cube root of denominator. And now we can apply log of the quotient, give you log of the difference of 2 log, sorry. So give you the log of x plus y squared minus log cube root of 10. Okay. Then now we're going to apply the formula. So give you log base 10 of x plus y 2 over 3. So m over n, so it will be 2 over 3. And over here I have 10 of 1 over 3 because it's invisible number 1 here. And now I can drop down the fraction, so it will become 2 over 3 log base 10 of x plus y minus 1 over 3 log base 10 and log base 10 of 10. Log base 10 of 10 give you 1. So my final answer will be 2 over 3 log base 10 of x plus y minus log base 10 of 10 give you 1. So give you 1 over 3 times 1, which is 1 over 3. Okay. So question is, are we going to stop here or we continue? Okay, thing is this. Maybe some of the students go ahead and break it down over here. We have a log of x plus y, and you go ahead and split up into log of x plus log of y. That would be wrong, okay, because we don't have the formula. So remember this. If you have log, if you have log base b of x plus y, it's not going to give you log base b of x plus log base b of y. Okay, this is a very common mistake. Try not to commit this mistake. Okay, so over here, that's it. We cannot do anything else. We cannot go ahead and break it down more over here. Okay, so that's it over here. Okay. All right. Example number 5. Okay. Sorry. Okay. Example number 5. We're still talking about expansion. Okay, how about this one? I have logs base 3, and the argument is pretty big. 27x. Okay. 27x to the third times square root y square minus 1 over y x minus 1 square. Alright, so we want to expand this. We want to break it down. So again, we see that the argument is a quotient. So it means we can go ahead and write it as the difference between two logs. So it will be difference between 27x to the third square root y square minus 1. I'm going to write carefully over here. This is to the third is for the x. Okay, minus log space y x minus 1 square. Okay. Okay, so right now we have 27 times x to the third times this radical. So I can break it down into log space 327 plus, using the property number 5, log base 3x to the third plus log base 3 of this square root. Okay, over here same thing, but because in front of the log we have minus, so you got to use the bracket or parentheses. So we just give you log space 3 of y time, because this is multiplication, plus log base 3 x minus 1 square. Okay. Alright, so 27 over here. If you notice, 27 is 3 to the third power. So I can break more, 3 to the third power. Now, number 3, I can use the third property. I bring down 3 to the front. And I'm going to use the radical formula I just showed you in the example number 4. I can rewrite it as rational exponent. So y squared minus 1 raise it to the 1/2. Okay. And now this one I'm gonna go ahead and distribute the minus. I cannot do anything with this because that's it. Minus, I can drop it down, number 2 here to the function -2 log space 3 x minus 1. Okay. Now again I'm gonna drop down number 3 here. You have log space 3 of 3 plus 3 log space 3 of x. I drop down a half over here. Log space 3 y squared minus 1 log space 3 of y minus log space 3 of x plus x minus 1. Look like over here we cannot do anything. Okay, so log base 3 of 3 give you 1 times 3 is 3 plus 3 log base 3 of x plus a half here. Alright, so over here this is important right over here. If you notice this is a difference of squares, you can go ahead and split it up. So a squared minus b squared will be a plus b times a minus b. This I'm going to keep it because we cannot do anything. Okay. Now I'm going to keep this one too. So log base 3 of x. This is log of the product one more time. I'm going to go ahead and split them up. But because over here is a half, because remember when you have a log of the product, give you the sum, and it gives you sum in front of the sum we have a half, so we gotta distribute to each of them. So this is log base 3 y plus 1 plus a half log base 3 y minus 1 minus log base 3 of y minus 2 log base 3 x minus 1. Okay, and now this is broken down. This is be broken down completely. Okay, there's nothing else we can break down. All right, that's it. Okay, there's nothing else. Okay. Now let's do the reverse process of expansion. The reverse process of expansion is called compression. So in the expansion process, we convert from product to the sum, from the quotient to the difference. In the compression process, or sometimes we call condensation process, we want to go from the sum to a product, or we want to go from a quotient, or from difference to the quotient. Now let's take a look at this one right here. So this all right. So we're gonna put a compression. Okay. Example number 1. Okay. Write the expression as a single logarithm, as a single log. Now I have something like this. I have log base 2 of 560 minus log base 2 of 7 minus log base 2 of 5. Alright, so we know that the difference over here, which is give you a quotient. Okay, so then the minus over here again give you another division. So you can do like this. First of all, you can go ahead, okay, factor the minus out. Okay. Okay, so before I continue, I just want to remind you this. In order to compress all the log together, the base must be the same. Over here the base 2, base 2, base 2. Okay, if over here base 2 and this is base 3 and this is base 5, you cannot do it. Okay, you can only compress the log with the same base. If you have different base, you cannot compress it. Alright, so right here we're going to do inside parentheses. So the sum of two log give you the log of a product, okay, which is 7 times 5, and now a log, the difference of two log, which is give you the log of the quotient between 560 over 7 times 5. Another reminder I want you to know is this. Because this log over here minus this, so this one go first, it means 560 must be on numerator. If you put 560 at the denominator and you put 7.5 on the numerator, it'll be wrong. So this one go first minus this, so this one must be on the numerator. Okay. Now we just need to simplify this, which is give you, simplify this, divide by 7, give you log base 2 of 16. Okay, and log base 2 of 16 is what? We all know that because we want to compress more, so we know that 16 is 2 to the 4. So I can apply the third property, which is give you 4 times log base 2 of 2. Log base 2 of 2 give you 1, so final answer will be 4. Okay. Example 2. Now, what if I have something like this? I have 1 over 2 natural log of x plus natural log x squared minus 1 minus natural log x plus 1. So we all know that the 1/2 over here I can bring to the top. Okay, we do it the reverse process. The reason you drop over here down, because when I drop it down I can simplify more. So see that there's only one number. I cannot go ahead and leave it like this. So I'm going to change it to log x to the half plus log x squared minus 1 minus log x plus 1. Remember, you always have to follow the PEMDAS rule. So if you have addition and subtraction, you gotta go from left to right. So addition over here, you cannot go ahead and do this one first. Okay, you're gonna do this one first. You're gonna go from left to right. So addition give you the product. Okay. Okay. All right. X to the half, I can change into square root of x. And now we have a log of the difference, which is give you a log of the quotient, which is square root of x squared minus 1 on the numerator, because this one go first, over x plus 1. But maybe some of you are going to stop right over here. You don't recognize the x squared minus 1 over here is a difference of square. So we can go ahead and change more. X plus 1 times x minus 1 over x plus 1. And now I can cancel the x plus 1. And what I have left is ln square root of x minus 1. Okay. Okay. Now let's do something more complicated. How about if I have something like this? Okay. There's some problems, very interesting problem, you know. Example number 3. Okay. It is example because this is because you know all the standard problem is like this. And I'm gonna move up a little bit more, see that we can do this problem. we try to challenge ourselves a little bit here. So I have log base 10 of negative b plus square root of b squared minus 4ac over 2a, and add it to the log of negative b base 10 minus square root of b squared minus 4ac over 2a. And I want to add the log. I want to add this log together. I want to compress them. I'm gonna make it simpler. Okay, so how I'm gonna do this? So we all know that addition of the log will give you the log of the product, so which is give you negative b plus square root of b squared minus 4ac over 2a times negative b minus b squared minus 4ac over 2a. Alright. Okay. So what we're gonna do now? It's this very interesting thing here. Now, think about this. Over here is minus b, so I can rewrite this as b squared minus 4ac minus b, okay, over 2a. Right, just switch the position, okay. And this one I factor the minus out, so become I factor minus out, so become b squared minus 4ac plus b, right, over 2a. Okay. Now, if you notice, this is two fractions multiply each other, so I can go ahead and multiply across, right? So 2 times 2, which is 4a squared. And another thing, if you notice, if you have so you have over here minus b, and you have something over here plus b, so that's the difference of square. So this is become minus a squared minus, right, b squared. There you go. Okay. Okay. Good. Because this is a plus b times a minus b, so it will be a squared minus b squared. Okay. Okay. So right now, I'm gonna go ahead and distribute the minus in. So if I distribute the minus, it will become positive b squared minus this square, b squared minus 4ac squared. Okay. Log. So this one I can explain as this is the square root of something square, give you itself, so give you b squared minus 4ac over 4a squared. Okay. Now I distribute the minus in, so give you log base 10 of b squared minus b squared minus 4ac over 4a squared. It's gone. So what I have left is log negative 4ac over 4a, and you simplify the 4, so you simplify one of the a, so you have log negative c over a. Okay, so we have log of negative c over a. What happened here? Let's see, we can keep it like this, or we can do something more. Okay. Well, I think I distribute them wrong over here, right? So it should be plus. Okay, should be plus here. So be plus here, so be plus. So we have log of C over A. Okay, log of C over A as the final answer. There you go. We don't want to expand it because this is compression. So originally we have a pretty complicated one, and now we compress into one log. So we have two log. Now we have only one log, and we have log of C over A. All right. So as long as I think that as long as you memorize all the property, you do a lot of problems, practice, then I'm sure you will be fine. Okay, so I mean on the test, I'm gonna give you one problem like this, maybe something similar to example 2 or something similar to all the example we here, and you just need to figure out what property you apply. Okay, then you should be okay. All right. So that's it for the lecture today. I'm gonna stop here. Please watch the video and let me know if you have any question, any concern. Then next time we will be learning how to solve exponential equation and log equation. Bye bye.